Hello, today we're going to be talking about a module that we have reintroduced to UTAPWeLS, which is the depth shifts module. We're going to start just with a plain project, and we have an LAS file that we want to explore, and we want to ultimately do some depth shifting before we go on and do anything else. So I'm just importing it, just dragging, dropping it there. Then it shows me all the logs that are going to be imported. They have been imported. Now we have a well that has the name of the LAS. We can open it. And very rapidly, we can just say, well, I want to see the triple combo, and boom, you just have it there. And you can get first some ideas. There's probably some sandstone here, and you get a quick idea of what's happening there. Now, to do the depth shift, which is what we care about today, we can either click on this icon or in logs, depth shift. And it's going to open the same window either way you do it. I'm going to make it a little bigger just so that it's better. And the way it works is you always have the formation zones. You have a track for depth. And then the third track, you always have a reference log. By default, it's going to be gamma ray, but you can choose whichever log you want to use as a reference. In some cases, it might be better to use density. So you can just modify it here. Whatever you want to use, it's OK. We're just going to use gamma ray. And then in any track after that, track 4 or any other, you're going to just add whichever log you want to modify. So I'm going to go with the shallow resistivity first. And this is how the plot is going to look like. You can see that it looks a little different. And the reason is because there's two lines right there, one showing the original log and another one showing the shifted log. Right now, nothing has been shifted. So it's one on top of the other, but we have something that we call anchors. You can add an anchor. This is just going to be so you can see it, and then we're going to do it. We're going to go a little more into details. So you add it, and then that's going to shift anything below by however much you decide to shift it. Then you can add another one, and you can shift. You can have stretch. You can have squeeze. You can have whatever you want. You can clear them all. You can delete one by one. You can do whatever you want with all of them. Of course, you're going to be zooming in a lot more when you're actually doing it. And instead of starting from scratch, we have implemented an algorithm called the COW algorithm, which is correlation optimized warping. And in a few words, it just works by segments. It takes different segments, and then it tests what is the best correlation, whether we're going a little up, or a little down, or where it was. We have 3 parameters that go with it. The segment length, the slack, meaning how much are you going to allow each segment to be shifted up or down, and the minimum correlation, so that if you see a slightly better correlation, well, maybe don't shift it, keep it where it was. By default, it's 0.7. The maximum is 1. If you put it 1, it's nothing's going to be shifted because nothing's going to be higher than that. If you make it 0, you may have too many shifts. So we want to avoid that. That's why we have that parameter there. You say, and the reason why we chose this algorithm is there was this paper in 2023 that tested multiple algorithms, and the one that gave the best results was this. It's not surprising. We know what we're doing in this case. We know we're looking for correlations, and an algorithm that is very transparently just looking for correlations. That's what it's doing. That seems to be the way to go. I know there's a lot of AI algorithms, a lot of hype, as we've seen in the past few years, maybe a decade already. And there might be cases where it's better to do it, but in general, we know we're looking for correlation. So it's not surprising that this algorithm was the best. It's the one we decided to implement. And if you don't do anything, you can just hit apply, and it's going to show you whatever anchors it thinks it's supposed to have. If you decide to have a higher correlation, it's going to select a fewer. If you make the segments larger, it's going to select fewer because the segments are longer, and they're going to be different. Some of them are going to be the same. Some of them are going to be slightly different, and then or significantly different depending on where you start. And then the slack is how much. If you make it larger, you're going to see some bigger shifts. Now, instead of looking at everything from afar, we can start looking at things a little closer, and we can see how the shift has happened in different locations. For example, this might be an interesting case. Here we can see, well, I can always go move and start moving them. So this one is saying it's making this shift, probably is trying to make this tip match here, but it's probably not the best. So you can play with it, and maybe it's not necessary. So if it's not necessary, you can just delete it, and you're gonna see well, here we see a very, very small shift, which you might decide it's necessary or not. And this is very clear why it was chosen. You can see that the very tip here it has a better correlation, and this curve, the curve that looks a little bit like a shade, the dotted curve has a better correlation with this part. So this small shift was selected. If you think it's relevant, you can keep it. Otherwise, you can always remove it. And there's always cases that are very clearly showing you what's supposed to be done. Let's say that I'm gonna say with the default parameter 16 and 2, say apply, and then let me look at, for example, I can see in this area might be, we can see a clear shift here. We see that this peak or that maximum is trying to make this maximum a little more aligned with that, and the same thing is happening here. It's thinking that this shift is better than keeping it here. It's up to you. This one seems like a good suggestion, but it's the entire segment, so you also have to be careful about what that implies. But in general, it's a very, very easy to use module, and we know that in many of these cases you will need certain level of intuition to work it. Now, this case we're just doing it with MOR1, but we can do it a little more complicated or a little more interesting. We can do it not just MOR1, but let's say that we also want MOR3. So we want the medium resistivity, and we also want MOR9. So all the resistivities. Then I can clear all of the shifts, and then I can apply it. What's interesting here is that the shift is applied not just to one of them, but all three of them. And not only that, but the algorithm is considering the shift of all of them. So the signal from all three resistivities is being considered as a correlation with gamma ray, and it's suggesting the anchors based on that. So here, this shift might be very realistic because it's, if you remember, it's compared to the previous case, it's a little more conservative, which makes sense. And you can probably rely on these shifts a little more. This shift is you can see how this maximum and not only the maximum, but this slope is correlated more with all three curves that are being shifted by the same amount always. The anchors do not change. On top of that, you can do it with multiple tracks. In general, it might not be that common, but it might be useful if you're doing it in many, many wells. You can just have, in this case, you could do, for example, neutron, and just apply it, and you have a different set of anchors for over here. And this is how it works. I hope you find it useful, and let me know what you think. Well, and after you have done the shifting, by the way, you save it in, and it's going to be saved in a different log set. So if we go to the main UTAPWeLS window, we can see that this well that has the original logs, and then that has the depth corrected logs. You can change the name, and you can add as many as you want. This can also be used as a tool to just combine multiple logs into the same log set. And that's it. Let me know what you think.